I'm gonna say something about how you can do group theory in a univalent way, and I'll say a little bit more about combinatorics. But before we do that, I want to show again something in my computer library, in my EGDA library. So where were we? Okay, so I was going to show again something about the library. Yesterday we made a start and we did something in Foundation, maybe in univalent Foundation, but I didn't show that there's actually much more in this library than only foundations. So there's some elementary number theory. As you can see, there's a lot of files that are about numbers. Then there's okay, so this univalent Foundation, this is gonna merge into the Foundation folder because it's all univalent, so I didn't want to make that distinctions. There's a little bit of category theory, something about the circle. Way not enough synthetic homotopy theory. There should be much more of that. And here in the groups, you see there's some distinction between abstract groups and concrete groups. And we're gonna learn. I'm gonna tell you about the distinction between abstract groups and concrete groups in just a moment. But as you see here, it's fairly minimal what is in there. So if you like to help, I will be very grateful. And the thing that actually is already quite substantial is the univalent combinatorics part of the library. So about the binomial types, that's what I showed you yesterday. It imports almost everything. And let's see if we can find the definition of a binomial type. It's here. It takes two types and then it says it has to be a binomial type of level. So it's let's see what that is. It is the type of all types in the component of the universe of level L at Y, and then it's this decidable embedding from Z, which is this type here, into X. So that's exactly the definition that I gave you. Oh, thank you. Sorry. Better? Yeah. Okay. So this is what it looks like, and that theorem that I showed you yesterday about the recursion should be in here, hopefully. Fairly sure oh yeah, here I do these cases empty over empty, with the empty type under, and this recursive equation. Apparently, it's what we did yesterday looks like this in the computer. Is this some code that does that computation, yeah, okay, so that's what I wanted to show you, and I wanted to show you something else. Let's see if we can go back. Yes, please. Oh, okay. Okay, so I'll go a little bit slower. Would that? Oh, okay, I get it. Okay, so where were we? We did some binomial types. Yeah, okay. So this is all imports. This is one big block of code. And here you have the code for the definition of binomial type, let's say. Let's ignore level for a moment. Then in this code, it first says what is the name of the thing that we are going to construct. Then it has colon, and then you specify the type of the thing that you're constructing. So first, always you give the specification, and then after you give the specification, you have a problem to solve, namely to construct an element of the type that you just specified. And that's what happens here. So here we say again, binomial type of level L at X and Y is defined to be, so the EGDA equality means colon equals. They made a big design mistake there, in my opinion, to not call it colon equals. because the equality sign is now taken and we cannot assert equality using equality. This is, yeah, I cannot get over that. Sorry. Anyway, so then the definition appears here, and it's this definition. Oops, sorry, I clicked on something. It's the formal version of what I had on the slides yesterday. So you take the sigma over z connected in z in the connected component of u at y. So that's b out y, and then you have to give a decidable embedding from z into x, and that's the definition of polynomial. So that's how that works. Let's go to something else. I thought it would be fun. I saw yesterday that there is a gap still in one of these files, and I don't like gaps in prime numbers. And there's some homotopy theory that you can apply to just show something about the definition of prime numbers. And I never formalized it, so I thought maybe we can do it right now. So this is the file about prime numbers. Here it says, what does it mean to be a prime? So first the name of the thing, then it's the specification. The predicate to be a prime is just a family of types over the natural numbers. And then for a natural number n to be a prime, it means that for every x in n, n is a proper divisor of x if and only if it's 1. Right, that's the definition of a prime. And then there is another definition, call it is prime easy, because I was out of inspiration. But this one says that a natural number is a prime if it's not 1, and if n is a proper divisor, then, if you have a proper divisor, then it must be 1. That's what this predicate says. This predicate here is defined to be any proper divisor is 1. So if you take this as the definition, then you have to be careful to also assert that your number is not 1. So this is an ugly definition. But I also have this definition 3. And 3 says that some space is contractible. And we can see now how we can use the ideas, like the very general theorems that we had about homotopy theory, and just apply them to the type of natural numbers, just for the fun of it, not because it's important or anything. It's early morning, so we can start easy. So what does this one say? This one says that the space of all proper divisors of n should be contractible. And that's also a definition of being a prime. If you think about it, 0 has a lot of proper divisors. To be a proper divisor is to be a divisor that is not the number itself. 1 has no proper divisors at all, so this one doesn't go in there. And then you go up and you notice that only that it's precisely the primes that have a contractible type proper divisor. So let's see. Now I'm in Emacs here, and the theorem is here. And the theorem that we should apply is that fundamental theorem of identity types. That's the one that allows us to show contractibility of something. So I'm just going to say fundamental theorem of identity types. And I don't want to conclude that something is equivalent to the identity type, but I want to go the other way around, that lets me conclude something is contractible. So I put the prime to apply the converse of the fundamental theorem. Remember, it's also an equivalent statement. Okay. Now it will need some arguments. I think probably 4 arguments. Yeah. Let's see. Yeah. And you mean this one? Sorry. Yeah, so I'm connecting with my laptop to Zoom, so it has to happen on this laptop. You're watching this computer? Oh, you have all my buttons on there. Well, let's see if we can do something about it. Oh, on this one. Yeah, thank you. View. Oh. Great. Thank you, thank you. Okay, so the first thing you have to do is give a natural number. That's probably n. Now we have to show that what n is a proper divisor of itself. That's crazy. Okay. Lambda x do something. No. Oh boy. What is this h that we have? H says that we have a prime. Let's see. 1. Okay. Sorry? Yeah, it's possible. Let's try though. What is the goal? What is this going to produce? Is prime n. 1n is proper divisor. Okay. Thank you. Yeah, so this one, if we put second projection here, then is 1n. Is that an assumption? Okay. So, so you see, this was a terrible idea. I don't know why. Oh, you're saying this should be the. That's what you're saying, right? This is a much better idea. And then raffle. Thank you. Yay. Yes. Yeah. Control X plus. Okay. Oopsies. Yeah, okay. So why should there be 1 here? It's that 1 is going to be the only proper divisor of the natural number, so it's going to be at the center of contraction. And this fundamental theorem is about center of contraction, so that's why that should be a 1. This one says we should assume an x. Then we should conclude some equivalence. Oh, no, we should look in goal 2. Okay, so we should again have some goal of the form PR2H x maybe. Oh no. Okay. Yeah, we have plenty of time. Why? Oh, is this PR1? Help. Okay. Do I need another lambda? Let's see. Goal 0 says that, yes, you need to assume that 1 is x, so let's assume a p. Okay. Okay, so maybe that helps. And then it's that one. Let's see if Egbert can solve this for us. It says we should put x here, and so this was an auto-solve from Egbert. Oops. Why is not happy? P. No, come on, int P. Okay. Cool. Okay, and the last thing we should show is there's some equivalence. There are some questions. Lambda, let's put an X here again. Lambda is really inconsistent about when it puts parentheses. And here we have some map, PR2, X, and V. Okay, so that's this map that we just constructed. And Agda wants us to show that it's an equivalence, but it's a map between propositions. So we're going to say is equiv is prop. This one's 3 arguments, I think, probably. Now it wants us to show that the identity type it1x is a proposition. That's by is set n1x. Because to be a set means that the identity types are propositions for every x and y. So this is a function that takes 2 arguments, 2 natural numbers, and says the identity type between those 2 is a proposition. Okay, 0. We want to show that is prop the negation of, oh my god. Is this, okay, so this means that to be a proper divisor is a proposition. I hope so. Is proper divisor. So that should be something. Yeah. Okay. And that's an n. This is by auto again, and that's an x. So good, we don't have to figure that one out. And now we have to construct a map in the converse direction, and we didn't use PR1h yet, so we're going to try that one. PR1h of something. This is a map. Oops. Let's get rid of this one. I wish it was, okay, lambda p2 something. I swear it is a PR1 of h of something, but Agda does not agree with me. Is it PR2? Oh. Okay. See, that's if you don't practice, then you have no idea what you're doing. So it wants us to prove that 1 is x. And in our assumptions, we have natural number. We know that n is a prime. We have x. And we know that p is a proper divisor of x. Okay, so we know h of x. This means that x is a proper divisor if and only if x is 1. I'm pretty sure we can do a PR of 1x here, and then a p. But now we have, yeah, why does this not just work? Oh, I see. Agda wants me to invert that equality. Okay, so that was stupid. Anyway, so we solved our goal, and then when you do that, yeah, sorry. Okay. Yeah, okay. So here's the statement. We claimed that if natural numbers is a prime, that's this here, then it has a unique proper divisor, and this is that statement that the total space of proper divisors is contractible. So this is what we proved. For every natural number, if it's a prime, then it has a unique proper divisor. So here we're going to define an element of the type above, and we assume a natural number, that's this one, and we assume that this natural number is prime. That's 8. Now we're going to define a term of type has unique proper divisor, which is the type is contour of the total space of proper divisors. And I say we apply our theorem from homotopy theory, fundamental theorem of identity types. We want to say something about equality with the natural number 1. So that's why 1 goes here. and then this function here, this theorem, has a lot of hypotheses, and that's what I have been filling out here. So yeah, so essentially what this says is you use that from the assumption that n is a prime, you know that any natural number is a proper divisor if and only if it's 1. So that's kind of what we're using here. This is the backwards direction, so if it's 1, then it's a proper divisor. And here again, if it's 1, then it's a proper divisor. We're using that assumption for some reason we needed it twice. And and then we needed to show that being 1 is equivalent to being a proper divisor. But both are propositions, so it suffices to have maps back and forth. But that's exactly from the assumption that that it's a prime. So. Yeah, they're both written in the same way. Yeah. 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 It isn't even if I want to. So the type usually goes here, but some types are defined also in exactly this way. For example, to be a prime, here the goal is to define a type. So here the construction looks like something that could have been a specification for another type. So yeah, it looks all the same. Yeah, that's the way it is. Okay. So let's. This is a new contribution. So let's do git commit. Primes have contractible type of proper divisors. And git push. Okay, apparently I did some more work in this commit, but we contributed something to the library. Okay, so now jokes aside, I'm gonna stop sharing this screen and go back to the presentation. Okay. Now, good morning again. Okay. Oh, of course I am starting at the beginning. Oops. Oh yeah. Yesterday someone asked me about the definition of an equivalence, and I didn't really have time to answer that. It's about why is that a Cartesian product, or if it's a fiberwise product. So if you look at the definition of being an equivalence, you first define the type of all sections of any map F. That's the type of functions equipped with a homotopy like that. And you define the type of retractions of F, the type of functions from B to A with homotopies like this. And the product of these two spaces, that is the type isequiv F. But this is, of course, a family of types that depends on F. So it's a Cartesian product, this product. But if you would do semantics, then you would probably take somehow the total space overall F and see it as a fiber product. So you can see it both ways, I think. But it's a Cartesian product for, yeah, I don't know if the person who asked me that question is in the audience. Okay, so let's go quickly forward. Not this anymore. Yeah, abstract and concrete group. Okay. Oh, yes, something I didn't show you. So in the library, I'm also defining like abstract polytopes, and that's because we're doing this kind of group here. Let's talk about this at some point. Okay, so to connect back to the previous lecture, we studied this type BSN, which was the type of all n-element types. And this is, of course, a pointed connected types. And we saw that it encodes the symmetry group on the set of n elements by just being the type of all n-element sets. So the idea of concrete group theory now is that if we want to study the symmetries of any objects, then what we do is we define the type of all such objects in univalent type theory. And this type will presumably be a pointed connected type. And its loop space is going to be exactly the symmetries of that object. So we saw that in the case of the n-element sets, we took the type of all n-element sets. This resulted in a pointed connected type, and its loop space was the automorphisms on the n-element set. But of course, you can then, once you have this idea, you can say, okay, the dihedral groups, they are the symmetries of the polygons. So how do you define the dihedral groups in homotopy type theory? Not by generators and relations. You define the type of all polygons. And I defined it in the library, but I didn't prove yet that its loop space is the dihedral group, because then you do have to define the algebraic version, which is of course possible, but I was focusing on other things. Anyway, so that's how you define symmetry groups. And so you can continue this idea. You can just say hyperoctahedral groups, they are the types of all n cubes for a fixed n. So you define what it means to be an n cube, and the type of all of these is going to be the classifying space of a hyperoctahedral group. And this is an idea. I think if I ever have a student, I will make him, or if I have a student that's interested in Rubik's cubes, I will make them define all the type of all Rubik's cubes and study that or something like that. So in principle, this is something that you can do. I do not claim that I've done it, but the point here is that we want to take as our definition of a group the type of pointed connected types, just to connect with this idea that a group should be symmetries of something, namely the base point of the pointed connected type. So a type is said to be connected if its set truncation is contractible. So an infinity group is a pointed connected type. An n group is a pointed connected n type, so that one group is a pointed connected one type, so it only has a fundamental group. And a group homomorphism is just a pointed map in both cases. So given an n group or an infinity group, we define G to be the loop space of B of G. That's the symmetry group. And it's acting on the base point of B of G. And it's a group just by the path operations. And our goal in this part of the lecture is to show, to construct the Eilenberg-MacLane spaces, but we're going to do that as the type of G torsors, because, here I want to say that there's a book being written, not by me, but by Ulrich Buchholz and Mark Bason, Bjorn Dundas, and Pierre Kanye and Ben Grayson, where they take this point of view on group theory, where a group is type of object that's automatically symmetries of that kind of object. And they develop all of group theory in this way, so it's really nice. And what I'm presenting in this part of my talk is their work. It's not my work, just because I find it very fascinating, and I'm formalizing it. So I've been thinking about it a lot. And this is going to go into that Unimath library that I just showed. What do they say? This is about the group actions. When you take this point of view that a group is a pointed connected type, then it's really easy to say what the group action is. is just a dependent type on your pointed connected type. And the action of the group, which is the pointed connected one type, on the type that should be acted on is just by transport, just by you construct this by the elimination rule for identity type. So this comes like automatically in type theory for free, basically, and that's why this theory is so nice. So a G type is just a map from BG into the universe. The type being acted on is x of star. Star is the base point of BG. And the action for any G in G, which is the loop space of B of G, you have the transport, which is an equivalence from x star to x star. And I shall often write just x for x star, even though x formally is the entire dependent type. But it's common to just write the type being acted on as the G set. So we saw yesterday an example of this. For any type B, recall that B out of B is the type of all types that are merely equivalent to this B. And then for any other type A, we can make this type family over U of B that sends X to the decidable embeddings from X to A. And this was in the definition of the binomial types. So this is an example of a G type where G is B out of B. So we're going to come back to that in a moment. Now, if we have a G type, then we can look at the type of its orbits. And the type of its orbits is just defined as the sigma type. It's again something really, really simple. And why does that work? Well, if we have a G in G, which is the loop space of B of G, and we have an X in this type that's being acted on, then from this X we obtain an element of this sigma type, namely star comma X, and G acts on it. So we also have star comma Gx. And because every type family in homotopy type theory is a vibration, by the path lifting property along the path G, which is a loop in B of G, we have this identification from star X to star Gx, which is an identification in the type of orbits. So what you see here is that things that are in the same orbit are getting identified. And that's why we think of the sigma type as a kind of a groupoid quotient of the type being acted on modulo G. And as you see, it comes for free again. So in our example from yesterday again, the decidable embeddings from B into A. This is again, so this is a type being acted on. And if we take the groupoid quotient modulo out of B, then we get exactly the binomial type. And now you can start seeing, if we do some basic calculations with cardinality, if B has m elements and A has n elements, then there are from B to A, there are this many. This is the following factorial. So there are this many elements in this type. This is well known, and this is the number n times n minus 1 until n minus m plus 1. And that's a factor m factorial too many elements. And now if we take that, that quotient by out of b has m factorial elements. So if we quotient that out and we divide here by m factorial, so by a kind of hand-wavy arguments, the cardinalities should work out. That's how I got to the idea of defining it that way. And then we got this definition. Yeah. At the very top, x. Oh, I think I made a typo here. Thank you. So here I should define x modulo g to be the type x in b g x x of little x. This is the correct definition, and that one is wrong. Thank you. Thank you. Okay. Yeah. Okay. That's that one. So in similar fashion, we can define the Stirling types of the second kind. Again, we consider an odd B action, namely now if X is a type that has that's merely equivalent to B, then we can look at the type of surjective maps out of A into X, and that's again that's an odd B action. And we simply define the Stirling type of the second kind to be the type of orbits of this action. And you can prove in a theorem that if A and B are finite types, then cardinalities work out correctly. The Stirling type of the second kind, AB, is finite and it has this many elements. So this is something you can prove. But this definition actually is not as nice as the one with decidable embeddings. For the binomial types, because you cannot in general prove the recursive law for the Stirling numbers. For this type, you have to assume that I think the type B has decidable equality, even to get the recursive law going, because these surjective maps they can mess up the equality. So I'm not going to prove that here. I just say that there is a little issue. But if A and B are finite types, then everything is cool, and we actually get the correct number of elements. So that's the message. We saw now what a concrete group action is. If we start with a concrete group action, then a concrete we start with a concrete group. Then a concrete group action is just a type family over that group. But now, if we start with an abstract group, the one everybody learned about in algebra class, then of course you can also say what a G set is, what it means for G to act on a type or a set. So we restrict to sets here, and a G set consists of a set X and a group homomorphism from G into the automorphisms on that set X. We write it with mu or with a dot or anything. And we're gonna need this definition in a moment. And a morphism of G sets from X to Y is a map from X to Y, but also it must respect the group action. So that means that square commutes. And such a morphism is an equivalence if the underlying map is an equivalence. And when you define a notion like this in type theory, I mean new, when you introduce it, the first thing that you do with it always is to characterize its identity type. Always. In homotopy type theory, you have to do it. So here, if we want to do univalence for G sets, we're going to need this notion of equivalences of G sets. So that's this theorem. For any two G sets, X mu and Y mu also, the type of identifications from the first G set to the second G set is the type of G set equivalences from the first to the second. So just as one would expect, so nothing very serious, but this is always gonna come in handy. That's why I'm saying it. And there's another thing I'm saying here, is that for any two identifications of G sets, P and Q, this alpha here respects the concatenation, so it turns concatenation of paths into compositional functions in the other order. And that's because we usually write the concatenation in the diagrammatic order and the function composition in the other order, but they respect each other. And this we're gonna need it when we want to show that the loop space of the type of G torsors is not only equivalent to the underlying type of the group, but actually has the same multiplication. We need a law like. So let's recall how we prove this. Any characterization of identity types passes through the fundamental theorem. So you prove that the total space of equivalences of G sets is contractible. And to do this, you simply say, we know that the type of y equipped with an equivalence from x to y is contractible. So kind of we distill this out from this this big sigma type. Note that this is actually 4 sigmas, 2 in the bottom and 2 here. So we have something contractible by univalence, and then you note that the type of actions of G on out of X, but the one that should come from Y, this is not a typo, such that some square commutes, that is also contractible by function extensionality. So what I'm saying here is this is a big sigma type, but you rearrange things and you recognize that two things are contractible, and they are bunched up and make something contractible. So that's why that works. And then the last claim follows, because if we now look at alpha of Raffel, so we got our equivalence, alpha. This will be the identity equivalence together with the proof Raffel that it respects the group actions. Morally, it's Raffel. If you concatenate from the left with Raffel, then that's identity, and composition satisfies the unit loss. So put all these things together, and you get the last claim that alpha respects this concatenation. So that's just that. Okay. Now we want to deloop our abstract group. So we start with our algebraic definition of a group. And we have just seen the G sets, and I didn't introduce them for nothing. I introduced them because we're going to use them. We now say that the principal G set, P of G, is the left action of G on itself. So every group acts on itself by multiplication from the left, and that's the principal G set. And the trick now is you can say that BG, or is defined to be the G torsors, is the type of all G sets that are in the connected component in the space of all G sets of the principal bundle. So, so that's what you can do. And by this previous lemma characterization of the identity type of G sets, of the universe of all G sets, we're gonna see that this definition indeed is a delooping of G. Okay, so that's the theorem here. We have a group isomorphism from the loop space of BG to G. And the previous theorem says we already know that this loop space is equivalent to the type of G set equivalences from the principal G bundle to the principal G bundle. So it's automorphisms on principal G bundle. So it's only a very small thing that remains to be shown. namely that this type of automorphisms here is isomorphic to the group G. So that's what we have to do now. So you see it was useful that we characterized that identity. Yeah. So, yeah. -1 truncation. Yeah, okay. So what we want to say is we only want to look at the connected component in the type of G sets of the principal bundle. But we don't want the equivalence to the principal bundle to be data, because otherwise this sigma type here would be a contractible type. And then we wouldn't be delooping G. So we want the entire connected component. And that's how you define that using truncation. Yeah. Yeah, so this is a little different than in set theory, but when you look at the whole category of G sets, or maybe at just the groupoids of G sets and isomorphisms, then you can look at the component of that groupoid with of the principal bundle, but you want to keep the automorphisms around. You don't want to kill them. Yeah. So that's what's going on there. Okay, so we need to give an equivalence. So we start with defining a map, and this map is given by evaluating at 1. So if we have a G set equivalence, then we have map from equivalences of G to itself to G. So we just evaluate at 1. And now the question is this an equivalence? And the answer is, of course, yes. The inverse map from G to, this is typo again. This should be G. The inverse map should map an element G to the right multiplication. So now you go to the other multiplication. But G set equivalences shouldn't be just equivalences, but they should also preserve the group action. And it preserved the action by associativity. I didn't really show that in the slide, but it's just associativity of G. That's the reason why this is a G set equivalence. And now is the question is every G set equivalence from PG to PG of this form? And the answer is yes, by this law H. We know that E of G is the same as EG1, but by H this we can take this G out now. So this is G times E1. So every such E is homotopic to multiplication by E1 from the right. And finally, the composites are preserved because if we look at FE1, then we get, of course, FE1. But again, we put the same trick. We put another 1 here. And then by the law of F, that F should preserve the action, we can take the E1 out and let F1 act on the right. So this means that the composite of F and E is sent to the multiplications. All is good. And this is all to show that we have isomorphism from PG to PG, not just an equivalence, but one that respects the group structure. So that's this is how you deloop a group. Any questions? Yeah. Oh, the action on this here. No, that would again be contractible. Because the quotient is just that sigma type. And the yeah. So if you have any B of G, then you have this G set that maps a little x to the identity star x. This is maybe the concrete version of the principal G action. And now, so let's call this one PG again. But remember just that we are now in the concrete, the world of concrete groups. And now P G modulo G is then the sigma type of X in BG star equals X. Let's put it with the identity type. But this is contractible. Yeah, no, there has to be a truncation there. I'm sorry. Okay. Now there's a little story one can tell about delooping group homomorphisms. So what we saw now is how to deloop the group, but actually what we want is then to construct an equivalence from the category of abstract groups to the category of concrete groups. And now we just define this functor on objects. We only set how you map a group to an abstract group to a concrete group. So you have to do this for group homomorphisms now too. But it's going to be useful to look first at how one would do this if we already knew the deloopings. So a group homomorphism from BG to BH, that's just a pointed map that we call BF. Yes, okay. So BG is the connected component of the principal bundle, which is a particular type, G type. So what we're going to do here is to map the G types to the H types along F. And this is a little bit weird because usually the map goes in the other way. I'm going to get some chalk. We have our group homomorphism F from G to H. This is the group homomorphism. And then G set and H set are categories. And we have usually F star going in this way. That's the usual direction. But now what we're looking for is to construct a left adjoint of that substitution or of this pullback. And this left adjoint is going to help us to deloop the group homomorphism. So we're still first going to look at the concrete case before we're going to do the abstract case, because the abstract case is a little bit harder to see what's going on and why we make definitions that we make. But if you want to go in the wrong direction, so to say, in the direction of the left adjoint, there's basically only one thing you can do, and that is if X is a G set, then we can look at for any Y in B of H. That's the assumption. We can look at the fiber of B of F at Y, and then have an X in here, and now look at X of pi 1 of X. That's the only thing that we can do. And that definition that I have there is basically this definition, but this fiber is now split out over 2 sigmas. Okay, so now in order to figure out what we have to do for the abstract case, we're gonna study this one for a second. So this one, if we think of it as a groupoid, then this sigma is a category of elements of the presheaf. Every G set can be seen as a presheaf, and this is a groupoid with one object. So there's one object here and a bunch of morphisms, and then here basically the morphisms come from H, and the elements here come from X. So the elements are of this form, morally, a star Hx and a star H prime. And what is the morphism from this triple to that triple? That's going to be a G. That's going to be a loop on this star. And then a P and a Q, where P says that if I multiply H with f of G, then that's H prime. And Q says that if I multiply X with G, or G and X, then I get X prime. So that's the kind of identifications that we have in there. So now what we're going to do is say that given an abstract G torsor X, so we move to the abstract world, we're going to look and say, okay, our goal is to define an H torsor, and the H torsor is going to consist of pairs, but quotiented by this kind of equality. So it's going to be pairs H times X, sorry. So that's H times X modulo an equivalence relation. And the equivalence relation says that Hx is equivalent to H prime X, precisely if there exists a G for which Fg is H and Fgh is H prime and Gx is X prime. And because because X is a G torsor, so it's merely equivalent to the principal one, there can be only one such an element X, so we don't have to worry that this is maybe not a proposition. So there's at most one such G. Okay, that's good. I put that in the slide. And there's a natural H action. You just act on the left-hand side of this Cartesian product. And then the theorem says that this is an H torsor, and it's an H torsor. Well, first you observe that being an H torsor is a proposition, namely to be in the same connected component as the principal bundle. And then, but we also have as an assumption that X is an H torsor, so X is in the same connected component as the principal bundle on G. But now we're trying to prove a proposition, so we can assume that X is the principal bundle. And under that assumption, things get a little easier, and you can basically go through this proof. Yeah. Let's just get to the takeaway of this part and move on to the next part. So I made 3 parts today because my talks are long. Is that the category of groups is equivalent, the category of abstract groups is equivalent to the category of concrete groups, and the category of concrete groups is defined to be the category of pointed connected one types. And in the symmetry book that I mentioned, that's going to be a very, very beautiful book. They exploit this equivalence, and they do all of group theory in this second category, the category of concrete groups. And that's going to be really, really nice. So lots of geometric ideas in there. And now I want to come back to very elementary mathematics again, to things that we saw in the first lecture. And we're gonna, I'm almost embarrassed to say, count the number of groups of order n, show that there's a finite number of groups of a finite order, any fixed finite order. But we're gonna do it with univalence. And again, this is kind of just for entertainment. It's not important work in any way. But just to see how univalence comes up in such questions. Why are there finitely many groups of order n? How can you see that? And you notice right away, if you think about this question, is okay, sure, there that if we look at the groupoid of groups of order n, there may be non-trivial automorphisms on any group of order n. So it's not going to be a finite type, even up to isomorphism. So we cannot just expect to prove that the type of groups of order n is a finite type. That's nonsense. But we still want to count up to isomorphism. And the question is now, how can univalence help us with that question? How can we count up to isomorphism with the univalence axiom? And this is not going to only apply to groups, but to any kind of structure. And how can homotopy theory help? So I'm just gonna throw some crazy homotopy theory at this problem. That is, yeah, shouldn't be necessary, but just for the fun of it, say. So I'm gonna make a definition. Type is pi n finite. That's my definition. If it comes equipped with an element of is pi n finite, which is defined recursively, we say that it's pi 0 finite if the set truncation is finite. So this means that it has finitely many connected components. And it's pi n finite if it has again finitely many connected components, but the identity types are pi n finite. So this is a recursive definition, and it's equivalent to say that type is pi n finite if it has finitely many connected components, and all of its homotopy groups at any base point up to level n are finite. So not assuming that there's a fixed base point, because I'm interested in the homotopy groups everywhere. This definition I just made up for the goal of counting up to isomorphism. So there's one simple theorem. I'm not going to prove this one, but the next one is to say that if B is a family of pi n finite types over a finite type A, then their product is going to be pi n finite. And you cannot really expect to improve on this condition that A is finite. So this is just saying pi n finite are closed on a finite product. But for example, I know the example that I had in mind is wrong. So let's just take this as a theorem, and they're closed on a finite product. But much more complicated is the version for sigma. So I'm first gonna prove a simpler case. If B is a family of pi 0 finite types, so each B of x has finitely many connected components, and it's a family over a connected pi 1 finite type. So it's a connected type, and the fundamental group is finite. Then the sigma type is pi 0 finite. So the sigma type has finitely many connected components. And we're going to prove this. And then we're going to generalize this. So this is just the lemma. So this is kind of the base case of an inductive argument later on. So first we observe that A is connected. So this means the zero truncation of A is contractible. And we're going to prove a proposition. So we can assume that A is a point. That's just by the universal property of the set truncation. Okay, so we assume our A is pointed. And now, because A is pointed connected, we have this fiber inclusion. And by the connectedness, it follows this is a surjective map. Okay. But if we truncate a surjective map, then we get another surjective map. So we apply the set truncation to the previous surjective map, and we get the surjective map here. And this is getting to start looking promising, because we have as an assumption that each B of A has finitely many connected components. And we have now a surjective map out of a finite type. So classically, we would be done here. We have a surjective map out of a finite type that's finite, and nothing anymore to show. But constructively, we still have something to prove. And the issue is that finite types have a well-defined number of elements. And if I have as my type 2 elements, but I identify them by some proposition P, then this type suddenly doesn't have a well-defined number of elements anymore, unless I can decide whether P holds or not. So the same trick that works classically doesn't work here. And we will have to show now by hand that the codomain is finite. But it's not so bad. The codomain is of a map out of a finite type is finite, if and only if it has decidable equality. So we only have to show that that this situation here, where the equality is maybe not decidable, cannot occur. So if we do decidable equality, then we're done. Oh, and it says I'm gonna do the proof by hand on the blackboard. Okay. Well, I still have 20 minutes, so is there an eraser somewhere? There? Oh, there's stuff there. Yeah, I don't want to make the blackboard wet, though. No, there's a dry cloth. Oh, cloth. Ooh. Yeah. Ooh. Okay. Okay. So we're looking at the identity type in there. Oh, I made notes here. So so basically, what we have to show is that the elements of the set truncation, they're kind of the form n x y, because it's a dependent pair type, eta x prime y prime. We only have to show that these are decidable, and then we're done. But this is, of course, equivalent to set truncation xy equals x prime y prime. And this is propositional truncation. And now we're going to use that the type A is connected and pointed. So this x and this x prime is merely equal to A. So this thing, it suffices to show that, so this thing is not equivalent, but it suffices to show that A comma y equals A comma y prime is decidable. So the is decidable. That's what we have to show. And of course, this thing here is equivalent to sigma p, a loop in A, and then transport in B, P, comma y. This should be y prime. This is set truncated. And when you sigma over set truncation over some type and you truncate it later, then you can also sigma over the truncations. So this we're gonna do. And now I'm gonna apply some homotopy theory trick, and I say let's look at A equals A, and we have a map into prop, and this map takes a P, a little P that's a loop on A, and it takes it to this transport B Py equals y prime. So this is a map from the loop space on A into the type of all propositions. That's why we truncated this. But this is a set. So we can factor this uniquely, and we get some big P that depends on y and y prime, and it maps from the set truncation into prop. And why am I going for this? Is that we have the assumption that A is pi1 finite. So I know that this is finite. That's why I'm going for this. So this sigma type here is, let's check, yeah. It is equivalent to P in the set truncation of A equals A. I hear this sound. And then P y prime of little p. And our goal is still to not to prove this, but to prove that it's decidable. But just to make a decision here. But now, now this one is decidable, so it suffices to show that this one here is decidable. Then we're done. But to prove that this one is decidable, we can go back to where this p came from, and it suffices to show that that these are decidable. And this is the case because this is this one here is equivalent to, let's see, eta transport b py. Oops, sorry for my handwriting. Equals eta y prime, and this is an identity type in the type b of a not, and we assumed that that b is a family of pi0 finite types, which means that there are finitely many of these, so its identity types are decidable. Okay, so that was some fairly tricky homotopy theory. Let's soldier on. So now we're going to get rid of the connectedness assumption and increase the pi finiteness level. So consider a family B of pi n finite types indexed by an arbitrary, so not connected anymore, pi n plus 1 finite type A. Then the total space is pi n finite. And if you would live in a classical world, we would only need that A is pi n finite by this argument that the fiber maps surjectively into the total space. But here we're gonna use pi n plus 1 finite. And I think Ulrich shared with me once an argument that that you can make this reduction if and only if the law of excluded middle holds. But I'd have to talk to Ulrich again because I quite forgot the argument. But I think it's something to do with this type here. So there's a no-go theorem there somewhere. Okay, so the proof of this thing is just by induction on the number of connected components of A. There are finitely many of those, and by induction on N. And yeah, you can easily write it out. The difficult part was the base case. So now how we put this all together to show that the type of groups of order n is pi0 finite. So we just want to know that there are finitely many connected components in the type of all groups of order n. And this is just because the type of all n element types is pi1 finite. It's connected, so it's pi0 finite. And its fundamental group is this n-symmetric group, which is finite. And actually, it's not only pi1 finite, it's pi n finite for any n, because above that is all trivial. And the number of group structures is just built out of pi sigma and identity type on the finite set, so that's also going to be finite. So the previous theorem applies, and we conclude that the type of group of order n is pi0 finite. And I have one last thing to show in ECDA, which is kind of cool. I formalized this whole argument. So here I formalized this, and what you get here is a function. It's computing now the whole library because we just proved something very low down there about primes. And so now it has to check everything again. But this will be quick, I think, I hope. The code doesn't show so nicely. Okay, so this code just goes through the semi groups first and then to the group. This might take a minute. So the same is done for monoids, a number of monoids of order n. And here I do it for groups of order n. So I show is finite is a group. So the group structures on the finite types, that's finite. That was a little argument, of course, because it doesn't really come for free. You have to prove that, okay, your type was built out of sigma and so on, but still at every step you have to keep track of the finiteness. But you can do that. Here's the theorem that we just saw for groups. Is pi finite the groups of order n? Actually, I prove here that it's pi finite for any k, but that's just the triviality. And then, then I get this. The number of groups of order n is a natural number. So this here I constructed a function from n to n. And this takes the number of connected components. So that's a function that returns a number from knowing that that the number of connected components was finite. So it's if you know in type theory that your type is finite, or a type, then you can extract from that the natural number, how many elements it has. So I just use that and get a function from n to n. And even even I also get the mere equivalence for every n. I know that there's some mere equivalence from the standard finite type with the number of elements, the amount of groups of order n, to the set truncation of the type of groups of order n. So so I know that this number is specified to be the number of groups of order n up to isomorphism. But then I ask that, so in this library I can't compute this number because I use univalence and function extensionality and so on. This number doesn't compute. But in principle, in cubical ECDA, if you put here the number 8, for example, the number of groups of order 8 is 5. So cubical ECDA should be able to tell me that there are 5 groups of order 8 if I just evaluate this function. So I told them that that I have this function that I'd like to try to compute it, and at first it didn't compute at all. And then after a few days of optimizing the code, it computed the number of groups of order 1, and it can do so after 1 minute computation, I think. But the number of groups of order 2 is already too many. for EGDA. So, and there should of course be only one group of order 2. So this function is completely useless, except that theoretically we have constructed the number of groups of order n. This is it for my lectures. I want to thank you all very much, and thank especially Dimitri for inviting me. It's really really big pleasure to speak to you, and hope to see you all again soon.
Thank you very much. So, any questions? Yeah.
It should be rather easy to define homotopy fixed points, because this is just a homotopical limit.
Yeah.
And then you have an easy way to formalize G equivariant homotopy theory, because just the equivalences are equivalences of all fixed points for subgroups of G.
Yeah, I think so, but I never tried. Yeah, thank you for the suggestion. But yes, if you have a G set from BG into U, X, then the type of fixed point is just the product X in BG X of X. So this is the other thing that comes extremely naturally. So to see that this is the type of fixed point, maybe you can say, okay, if I have such a function that selects an element out of each of my types, then so this one has one base point. So I get my my x0 in x of star, and it's a fixed point because if I transport along a loop, well, this function is going to respect equality, so it's going to respect paths, and it gives me a path from f after transport to the original value. So this is the type of fixed points, and yeah, it's an excellent suggestion, but we haven't yet gone that direction. But I would very much love to. Yes.
Other questions? No? Okay. So, thanks again.